So, good evening, everyone. Welcome to the problem solving session and the doubt clarification session for the NPTEL online course on the water and wastewater treatment. So, we are into week 11 now. So, as you all know, the course instructor is Dr. Bhanu Prakash. He is from IIT Roorkee, and I am one of the teaching assistant. My name is Akash Shah, and I'm a PMRS scholar at the Department of Civil Engineering at IIT Madras, where I'm pursuing my PhD in environmental engineering. So we will quickly go through the contents of this week 11's lecture. So as you all know, in this week we have covered 3 to 4 topics. We started with adsorption, where we learned what is adsorption and what are the various mechanisms, then how activated carbon is being used and what is the process of absorption, and then about the GAC breakthrough curve. And then we looked into the adsorption isotherms, where we learned about various models of adsorption, starting from the linear, Langmuir, Freundlich, and the BET isotherm. Then the next topic that was discussed was about ion exchange process, where we learned about the various types of ion exchangers, their selectivity, and so on. And the next topic was about the nanofiltration and the reverse osmosis processes, the various parameters and the properties. And at last, we learned about the removal of the ferrous and the manganese ions from our system. So this was the brief overview of the lectures that were conducted this week. So I have some multiple choice questions and also some subjective type of questions for you so that you can attempt your assignment problems. So we will go through each of them one by one. So first we will start with the MCQ problems. So I will show the first question. So this is the first question. It says that activation of carbonized material involves. So here we are talking about the activation for the adsorption process. So it says activation of carbonized materials involves exposure to the steam, pyrolysis, formation of pores and fissures, all of the above. So we have 4 options. We have to find out which of these following are a part of the activation process. So we have to keep in mind that here we are only talking about the activation process. Okay, so please go through the question once again and try to attempt the question. I'll wait for some time. So let me discuss regarding the question. So it's when we are talking about activation, so there are uh, 3 to 4 things. So the first thing will be the exposure to the steam. So option A is definitely correct because we expose our carbonized material to some steam. So option A would definitely be the correct option. And after that, it is followed by the formation of some pores and fissures. So it increases the surface area. So in that way, option C is also correct. So in this question, if you see option A and option C is correct, option B and D are not the answer for this question. So the correct answer is option A, exposure to the steam, and C, the formation of pores and fissures, which is followed by the exposure. But if we talk about the pyrolysis, if we go to the detailed answer, so pyrolysis is a part of the carbonation of the material. So when a carbonaceous material is heated in oxygen starved environment, to liberate the carbons, it is known as carbonation. So pyrolysis is not the part of activation, rather it is a part of the carbonation, whereas the exposure to the steam to cause the pores and fission is a part of the activation. Okay, so I hope you have understood it. Let me go to the next problem. Okay, so the next question says that which of the following statements are correct? So we have 4 statements here. The first one says granular activated carbon or GAC is a heterogeneous media for adsorption. Option B, only natural and non-synthetic organics can be removed by GAC. Option C, the more hydrophilic a compound is, the higher its tendency to get absorbed to GAC. And option D, polar compounds are typically not removed by absorption by GAC. Okay, so these are the four options we have. So you have to tell me which of the following statements are correct. So basically we are talking about the absorption of GAC. So whether it's a kind of heterogeneous media or which kind of organics can it remove and what will be the properties, whether it's better to have a hydrophilic property of the compound or hydrophobic, and what type of polarity, is it a non-polar or polar compound. Okay, so think about it for some time and then we will discuss about the answer. Okay, so let's see what is the solution. So the just a second. Okay, so the correct answer is option A and option D. So why is that? So option A says that it is a heterogeneous media for absorption. So it's a well-known fact that GSE is a heterogeneous media, not an homogeneous media. So option A would definitely be correct. Then second says only natural and not synthetic organics. So it says that synthetic organics cannot be removed. So which is false. Synthetic organics can also be removed. Then option C, the more hydrophilic a compound is, the higher tendency to get absorbed. This is incorrect because if the compound is hydrophilic, then it would like to stay in the aqueous mode only, or rather in the solution. It will not get absorbed onto the solids of GAC. Okay, so the more hydrophobic a compound, the higher will be its tendency. Okay, not hydrophilic. So definitely option C is incorrect. And if we talk about option D, so polar compounds are basically hydrophilic compounds. So again, option C, if we have just discussed in option C that hydrophilic compounds are not removed easily by the absorption of by GAC. So polar compounds are typically not removed by absorption by GAC. So option D is correct. So as you can see, option C and D are related to each other. So basically, whenever there is a hydrophilic compound, it will like to stay in the liquid phase only. Okay, so it will not get absorbed easily. And polar compounds are mostly hydrophilic. And option B is also incorrect. Option A is correct. So for the second question, we have the answer as option A and option D. Fine. I hope it is clear. We will move forward to the next question. So again, it's a true false type of question. So it says that in general, soil possesses cation exchange capacity due to the presence of negatively charged clay particles. Is it true or false? So here we are talking about the soil. So whether or not it contains any cation exchange capacity. So the statement is regarding that. So we have to tell whether it's true or false. So if we discuss about this, then definitely Option A is correct because it's true, because soil contains many clay particles which are mostly negatively charged. So whenever a negatively charged particle is present, it will possess some cation exchange capacity. Okay, so option 3 for option A, true, is correct. So for third question, it is true. Let's move to the next problem. Again, a true false type. Reverse osmosis or RO membrane fouling occurs due to chemical scaling. So it's a direct thing. So just think over it whether it's a true or false. I'll give you some time to think about the answer. So here if you see, option A is correct because this statement is also true, because definitely the RO membrane will be subjected to chemical scaling because the presence of very dissolved organics. Okay, so these pollutant or constituents can cause the chemical scaling. Okay, so it is true, option A. Okay, now we will move forward regarding the match the following. So we have two types of absorption given on the left hand side, which is the physical and the chemical absorption, and some of the characteristics. So the characteristics mentioned are non-specific binding, specific exchange of electrons, typically non-reversible, reversible, common type of adsorption mechanism, rarely used in wastewater. So some characteristics are given for adsorption processes. So we have to match with the corresponding type of adsorption, whether it's physical adsorption or chemical absorption. So try to match it with the correct type, and then we will discuss the answer. So let's discuss about the problem. So if we see physical adsorption, basically it's a reversible type and there is non-specific binding, and it's very commonly used in the adsorption mechanism. Okay, so for physical adsorption, the correct characteristics will be option A, non-specific binding, option D, it's a reversible process, and option E, a common type of adsorption mechanism. Now, if we see about chemical adsorption, definitely there is a specific exchange of electrons because it makes some bonds. So there will be exchange of electrons for chemical adsorption. Also, since there is a chemical bond there, so typically it's a non-reversible type. And at last, these are rarely used in water treatment because most of the water treatment processes, it is governed by the physical adsorption, which is the common type. So for type 2 chemical adsorption, the correct characteristics are B, C, and F. So if you see the answer, it is option A, where one physical adsorption is matched with A, D, E, and two chemical absorption is matched with B, C, and F. So this is what about the fifth problem for match the following. We'll move forward now to the next problem. Again, it's a match the following type. So basically, we have three types of groups present, which is the backbone group, cross-linking group, and an ion exchange group. So by seeing the figure, we have to match the corresponding group. So large chains are given. So we have to identify the portion which is marked in green. So in the first figure, it is a COOH bond, and then there is a benzene ring, and then there is a long chain of hydrocarbon. Okay, so we have to match with each of them to the correct group. Just think about it, then we will discuss. So if you see, the backbone group will be the long chain of the hydrocarbon, which is given in the third figure. Cross-linking group will be same as shown in figure B, whereas the COH is an exchange group. So the correct option would be option B, where we match 1 to C, 2 to B, and 3 to A. Okay. So directly we can say, because COH is definitely an exchange group, and a long hydrocarbon chain can be acted as a backbone group, and the other one can be a cross-linking group. So option B is correct. Let's move forward. So the question says that consider the following statements. So two statements are given. Of statement 1 says the correct sequence for attraction to a typical ion exchange resin for calcium, magnesium, and strontium will be strontium 2 plus followed by calcium 2 plus and then magnesium 2 plus or magnesium ion. Statement 2 says that, or B statement says that, the affinity of the ion exchange material is higher for the ions with smaller hydrated radius. So this was about statement B. Now we have to select the correct option. Option A says statement A is correct but B is incorrect. Statement B says A is incorrect and B is correct. Statement C says both statements A and B are correct and B is the correct explanation of A. Statement D says both statements A and B are correct but B is not the correct explanation of A. So you have to tell me which of the options is correct. There is a little typo error in this, not typo, but rearrangement problem. So after B, there is option C also in the same line. So we have to say whether the correct sequence of attraction of a typical ion exchange resin will be followed as strontium, calcium, magnesium, and also the affinity of the ion exchange material will be higher if there is a smaller hydrated radius. So please think over it and tell me which of the statements is or are correct. I'll wait for some time. So here we have to bring the periodic table into picture. So if we see in the periodic table, so as we go down in a column, okay, so mostly the charges will be the same, whether plus 1 or plus 2. So if we see down in the column of calcium, magnesium, and strontium, so we can see that as we go down the column, the unhydrated radius will definitely increase as the number of electrons in the atoms increase. So the size of the unhydrated atom will increase, but the size of a hydrated radius will be decreasing. Why is that so? Because ions larger in size and with typically low charges bind to the water molecules less tightly and have a smaller hydrated radius. So this is the reason. So both option A and B are correct because strontium, though it has the maximum number of electrons, the unhydrated radii will definitely be the largest, whereas the hydrated radius will be the smallest. And also, if smaller the hydrated radius, the affinity of the ion exchange material will be higher. So option B is correct, as well as the correct explanation to option A or statement A. So here the correct option is statement C, which says both statements A and B are correct, and B is the correct explanation of statement A. Fine. So this is about the seventh question. Now we will move forward to the eighth question. Okay. So let's see the eighth question. It says that absorption of toluene onto the activated carbon obeys the following Freundlich isotherm equation. So absorption of toluene, which is our pollutant, is given on the activated carbon as a Freundlich isotherm. So it says that Q toluene is equal to 73.4 C toluene to the power 0.365, where C is in milligram per liter, Q is in milligram per gram. Now it says that a sample containing 0.65 milligram of toluene will be treated in a batch process to reduce the concentration less than 0.02 milligram per liter. So initial concentration is 0.65, final is 0.02. So now we have to find out the required activated carbon dose in milligram per liter. Okay. So we have to find out the dosage of activated carbon required for this absorption. So kindly go through the question again, take a screenshot, and then we will see the solution. I'll wait for a minute for you to take down the problem and the related input data given. So C naught is 0.65 milligram per liter, CE is 0.02 milligram per liter, and Q total equation as Freundlich isotherm is given. So we have to find out the activated carbon required. Okay, so let's try to solve this problem. Okay. So problem number 8, it is given that my Q toluene is 73.4 C toluene to the power 365. So the value of C toluene, that is the equilibrium concentration or the final concentration. So 73.4, the C toluene is given as 0.02 to the power 365. Okay, so if we solve this, we will get 17.60 milligram per gram. Okay, so Q toluene is nothing but 17.60 milligram per gram. Now once we get Q toluene, we will apply the mass balance because the total concentration of the toluene will be conserved in the system. Okay, first it was totally in the liquid, then it get partitioned into the liquid and the solid phase. So now by applying the mass balance, we know that the concentration of total toluene, okay, will be equal to the toluene, sorry, in the system plus some kind of adsorption. So it will be Q toluene into the just a minute. Just wait for a second. Okay, sorry for the delay. So if we apply the mass balance, we see that the total toluene concentration will be partitioned into the toluene concentration in the liquid after adsorption and whatever is absorbed on the GAC. So this will be the concentration of the GAC or the activated carbon. So this is 0.65. The final left is 0.02 plus Q value is 17.60 into CGAC. Okay. So my CAC, if I solve this, I'll get it as 0.0358 gram per liter. Or we can say that CAC is my 35.8 milligram per liter. So this is my final solution. Okay. So what we did, we used the Freundlich isotherm that is given to find out the Q total value, Q toluene value, and then we applied the mass balance. Okay, because in my system, suppose this was the liquid, so my first concentration was 0.65. Okay, so later let's see in case 2, in which I have given some granular activated carbon. So some portion of the contaminant will be absorbed on this thing and the final concentration in water will be 0.02. Okay, so like this we can solve this problem. Okay, please note it down and then we'll move forward to the next question. Okay, so I hope you have noted it down. We will move forward. So the correct answer is 35.8 milligram per liter. Next problem. Select the correct statements regarding chemical and physical adsorption. So we have four statements here. So we have to find out which of the following is correct. So statement A says, if the pore volume is taken up by pores of different sizes, then efficiency of adsorption is decreased. Then B, physical adsorption, the forces of attraction include only physical forces and exclude covalent bonding. C, when chemical adsorption occurs, the media generally can accumulate multiple molecular layers. Option D, metal oxide surfaces can adsorb humic and metals. So these are my four statements. You have to find which of the following is correct regarding both chemical and physical adsorption. Okay, so please think over it. So if you see, option A would be correct, because if the pore volume is taken up by pores of different sizes, then the efficiency will definitely will increase, not decrease. Okay, because various sizes pores are there, so the kind of materials will be absorbed will be more, and hence the efficiency of the adsorption will be increased. Then about option B, physical absorption. So option A is incorrect. Okay, because it will be increased. About option B, it says about physical adsorption, the forces of attraction will include only physical forces and exclude covalent bonding. So it is also correct. It is correct. So option B is correct. And if you option C, option C, so it says about chemical adsorption, the media generally can accumulate multiple molecular layers. So it is incorrect. Mostly it is a single molecular layer because there is a bonding. And option D, metal oxide surface can absorb humic metals. So this is correct because metal oxide surfaces generally absorb the humic particles and the metals. So option B and D are correct. Okay. So this was about question number 9. Let's move forward. Select the correctly matched pairs regarding causes of adsorption. Okay. So we have dislike of water phase, hydrophobicity, van der Waals forces, surface charge integration, electrostatic forces, physical interaction, chemical forces, pi and hydrogen bonding. So these are my four types of options given. So we have to see whether it is correctly matched or not. So please try to think about the correct option. So if you see here, uh, dislike of water phase, that is actually called as hydrophobicity, hydrophobia rather, whereas hydrophilic compounds are having a liking of water. And so option A is correctly matched, whereas option B, it says van der Waals forces surface charge interaction, whereas van der Waals forces are some physical attraction. It's not a surface charge interaction, it's a physical attraction, whereas the electrostatic forces are some surface charge interaction. Okay, so option B and C are mismatched with each other, so both are incorrect. And at last, about the chemical forces, it is a pi and hydrogen bonding. So option D is correct. So here option A and D, which says option A as dislike of water phase as hydrophobicity, and option D as chemical forces for pi and hydrogen bonding. So option A and D are correct. Now let's move forward. So here again we have four statements around as per the ion exchange process. So we have to find out which of the options are correct. Option A, weak acid resins have lower pKa compared to strong acid resins. B, option B, it is easier to generate the weak acid resins compared to strong acid resins. There is strong attraction to singly charged ions due to smaller hydrated radius. In a resin column, the exchange reactions begin to saturate the upper levels before the lower levels, given that the direction of flow is from top to bottom. Okay, so these are my four statements. So you have to find out which of the statements are correct. Just think over it, then we'll discuss about the problem. So if you see statement A, weak acid resins have lower pKa compared to strong acid resins. So generally pKa is defined as a negative logarithm of the Ka value. Okay, so definitely weak acid resins will have a pKa greater than the strong acid resin because it's a negative logarithm. So option A is incorrect. It is easier to regenerate weak acid resins compared to strong acid resin. So this statement is correct because the weak acid resins exhibits a much higher affinity to the hydrogen ions than the strong acid resins. So it allows the regeneration of the hydrogen form with significantly less acids is required for the strong acid resin. So definitely option B is correct. Then there is a stronger attraction to singly charged ions due to smaller hydrated radius. This is wrong because if more the charge, the attraction will be more. So it's not as per singly charged ion. If the if it's a doubly charged or tertiary charged, so it will be much more. So option C is incorrect. Whereas option D, it is correct because whenever you use a resin column, the upper levels will tend to saturate earlier before the lower levels because the flow is from top to bottom. So upper layers will saturate before than the lower. So option B and option D are correct. Okay. So this was about the 11th problem that we discussed. Now let's move on to the next problem. Select the particles which are specifically removed by nanofiltration process but not by filtration process of higher filtration or pore size. Okay, so here we have to think only about the nanofiltration, like which of the particles will be removed by only nanofiltration but not by the higher filtration processes. So we have option A as algae, protozoa and bacteria, option B as colloids, small colloids, option C as divalent ions and dissolved organic matter, and then the monovalent species. So you have to find which of the options are correct. Think about the problem and then we'll discuss. So if we discuss about the algae, protozoa and bacteria, so many of these microorganisms can be removed by the filtration of higher pore size and even some small colloids are also removed. Okay, whereas the divalent ions are only removed by the nanofiltration processes. So option C is definitely correct because it talks about the divalent ions and the dissolved organic matter. So these are typically removed by the nanofiltration processes, whereas the monovalent species are not particularly or very poorly removed by the nanofiltration processes. So option D is also not correct in this context because these are poorly removed by the nanofiltration process. So the only correct option here is option C, that is the divalent ions and the dissolved organic matter. Okay, so this was about the nanofiltration process. Now next problem, you have to match the following process with the characteristics. So we have four types of processes: electrodialysis, reverse osmosis, nanofiltration, and thermal distillation. And we have four characteristics. You have to match them accordingly. So the characteristics are: uses heat and converts the water into water vapor. Some of the operational challenges are scaling and fouling. It is a process which is electric voltage driven and not pressure driven. And then movement of water from low salt concentration to higher salt concentration by applying pressure. So just think over it and match the proper process with its characteristics. So here if we see, discuss the problem, then electrodialysis is basically a electric voltage driven process. So for option A1, it's C. Reverse osmosis, so it is about the movement from low salt concentration to a high salt concentration by applying pressure. Okay, so it's reverse osmosis. Then option 3, nanofiltration, it is challenged by the scaling and fouling, so it's matched with B. Then thermal distillation is a process which uses heat and converts the water into water vapor. So the correct option here is option B, 1C, 2D, 3B and 4A. Okay, so this was about question number 13. Now next problem. Select the correct statements regarding reverse osmosis theory. So we have to talk about the reverse osmosis theory here. Chemical scale fouling in membranes occurs due to increased concentration of relevant ions in the concentrate. Okay. Solute rejection is lower for highly charged molecules but higher for larger molecules. Volumetric flux of water is given by JW is equal to KW into delta P by delta Y. Membrane material is susceptible to biological degradation and degrades with free chlorine concentration below 1 mg per liter. So these are the four statements given. You have to find out which of the options are correct. Okay. So go through the problem once again and we'll discuss it later. So if you see here, the chemical scale fouling in membrane will be increased by increased concentration of ions in the concentrate. Okay. And if we talk about the option B, solute rejection is lower. It is saying lower for highly charged molecules, but generally the solute rejection is higher for highly charged molecules. So option B is incorrect. Option C, volumetric flux is given by the equation. So the equation given is definitely correct. So option C is fine. Now talking about option D, it is saying that it will degrade the membrane material if the concentration is below 1 mg per liter. So this is incorrect. It is true when it is above 1 mg per liter. So if the free chlorine concentration is above 1 mg per liter, it will try to degrade the membrane material. So option B is incorrect. So here option A and option C are correct. Okay. So chemical scale fouling is due to the increased concentration of relevant ion, and the volumetric flux is given by JW is equal to KW into delta P minus delta pi. So this is option, correct option for 14th question. Now next problem. Select the ways in which both iron and manganese removal will be done. So we have to find out in which way both iron and manganese can be removed together. Okay. So we have five options here: lime soda ash softening below pH 9.8, chemical oxidation, aeration, lime soda ash softening above 9.8 pH, and then sequestration. So try to answer this problem and then we'll discuss. So if we talk about the lime soda ash process of softening, then the pH must be above 9.8 to remove both iron and manganese. So option D is correct. Chemical oxidation, so chemicals like chlorine or potassium permanganate can be used to remove iron and manganese. So option B is correct. Whereas aeration can only remove the ferrous but not the manganese. So aeration is incorrect. And about sequestration, so what is sequestration? So when phosphate chemicals are added to water to bind with and sequester the ferrous and manganese and preventing the later precipitation. So this is known as sequestration. So this can also be used to remove the iron and manganese. So we can see that option B, D and E are correct for this problem. So with the help of chemical oxidation, lime soda ash softening above 9.8 pH and the sequestration process can be used to remove the iron and the manganese. Okay. So I think these were all the MCQ type problems which I had. So now we will solve some subjective problems. So let's start with the first one. So it says that as a result of effluent chlorination, the amount of chloroform formed was found to be 0.12 milligram per liter. How much powdered activated carbon will be required to treat an effluent flow rate of 4000 meter cube per day to reduce the chloroform concentration to 0.05 milligram per liter? The Freundlich adsorption isotherm coefficient for chloroform are Kf is equal to 2.6 and 1 by n is given as 0.73. Okay, so all the data is being given. So please go through the problem once again, note down the parameters, the relevant data given to solve the problems, and then we will discuss how to solve it. Okay. So I'll give you some time to take down the problem. Okay, so we'll see how to solve this problem. So this is question number 16. So we'll use some equations related to absorption. So we know that, so the first equation very well known, Q is equal to V by M Ce minus C naught. Okay, and another equation we have is Q is equal to, or we can write X by M is equal to C Kf Ce to the power 1 by M. So these are my two equations. Okay, equation 1 and 2. Fine. So now if we, so from 1 and 2, we can write something it like this, that V by M will be equal to Kf Ce 1 by N divided by Ce minus C naught. Okay. So Kf value is known, 2.6 into C is 0.05 to the power 0.73, 1 by N value is given, and in the denominator we have 0.05 minus 0.12. So it will turn out to be minus 1.74 liter per gram. Okay, it will be in minus because of those terms. So basically we have C naught is equal to 0.12 milligram per liter. We have Ce as 0.05 milligram per liter. We have Kf as 2.6 and 1 by N value is 0.73. Okay, so all this information were given in the problem if you have seen. So once V by M is known, so my M by V, if we just take the positive value, we'll get it as 1 by 4.71. So it will be 0.24 gram per liter. Okay, so I got the M by V value. So this is the mass per volume. So now at last, the amount of carbon required to treat. So we have a discharge of 4000 meter cube per day. So the amount of carbon required, or we can say PAC required, it will be equal to, so my mass per volume is 0.24 gram per liter into the discharge 4000 meter cube per day. Now 1000 liter per meter cube divided by 1000 gram per kg. Okay, so these are some unit conversions. So my PAC required will be 960 kilogram per day. Okay, so this is my PAC required. So it's a pretty simple and direct problem. So what we did here is, so we know two equations for absorption, that is Q is equal to V by M C minus C naught. So this is my first equation, and then Q is equal to KFC on to the power 1 by N. So these are the two equations very well known. So from that we will calculate the V by M by rearranging it and putting the relevant input parameters. So later we will calculate the mass per volume, that is 0.24 gram per liter, and then by multiplying it with the flow rate we will get the answer. Okay, so I'll zoom out and you can see the solution again and note it down. Okay, so I hope you have noted it down. We'll move forward. So 960 kilogram per day was the correct option. Now 17th problem. A fixed bed activated carbon adsorber has a fast mass transfer rate and a mass transfer zone is essentially a sharp wavefront. So this is the characteristic. Assuming that the following data apply, determine the carbon requirements to treat a flow rate of 1000 liters per minute and the corresponding bed life. So here we have to find out the carbon required and also the corresponding bed life to treat 1000 liters per minute. So compound is trichloroethylene, that is also called as TCE. Initial concentration 1 gram per milligram per liter. Final is 0.005 milligram per liter. The density is given of GSE as 450 gram per liter. KF value is 228. Another parameter 1 by N is 0.62, and the EBCT is given as 10 minutes. Okay, so ignore the effects of biological activity within the column. So this is also given. So here we are only focusing about the absorption. So hence we are removing the biological activity. So now we have to find out the uh, carbon requirement and the bed life. So just note down the problem. We will see how to solve it. Okay, so we'll see the solution for this. Just a second. Okay, so this is problem number 17. So first, estimate the GSE usage rate for the trichloroethylene. The GSE usage rate is estimated by, I think there is some problem with this pen right now. Okay, it's fine. Usage rate is estimated by mass of GSE by QT is equal to C naught by CE by QE. So this is the general equation. So we can write is as per the adsorption isotherm KF C naught 1 by N. Okay. So or MGSE by QT is given as, so if you substitute the values, we have C naught as 1 milligram per liter minus 0.005 milligram per liter, then 28 milligram per gram into 1.0 milligram per liter to the power 0.62. Okay, so we have substituted all the values, so we'll get it as 0.036 gram GSE per liter. So this is what we get. So now we have to determine the mass of carbon required for a 10-minute EBCT. Okay, so EBCT is given as 10 minutes. So mass of GSE in bed required will be equal to the VB into the density of GSE. Okay, so VB can also be written as EBCT into the discharge into PGAC, rho GAC rather. So EBCT is 10 minutes, Q is 1000 liter per minute, and density is 450 gram per liter. So we'll get the carbon required as 4.5 into 10 to the power 6 gram. So this is my carbon required. After solving, we will get this. Okay, so the first part, which is the amount of carbon required. So what we did, we used this equation. We used this equation to find out how much gram per volume is required. And then when we multiplied the ABCT into the Q, into the PGAC value, we got it as, or rho GAC value, we got it as the 4.5 10 to the power 6 gram. But now determine the volume of water treated, because you have to find the bed life. So using a 10-minute EBCT. So how much water will be treated? So volume of water treated is equal to the mass of GAC for given EBCT. So whatever the mass of GAC is given for the EBCT divided by the GAC usage rate. Okay. So the mass of GAC we have just calculated gram, and the usage rate, as we all know, 0.036 gram GAC per liter. So this is the GAC usage rate we have calculated in the first part. So we'll get it as 1.26 into 10 to the power 8 liter. So this is the volume of water. So the total mass divided by the usage rate, we will get the total volume of water treated. And at last, the bed life will be equal to the volume of water treated divided by the flow rate. So 1.26 into 10 to the power 8 liters divided by 1000 liters per minute into 1440 minute per day. So we'll just change the minute into days. So it will be 87.5 days. So pretty simple. I will explain it once more. So first we have to find out the GAC usage rate. So this is given by this formula. So every parameter is known. So we got the usage rate at 0.036 gram per liter. Then we will find out how much carbon is required. So mass will be equal to the volume into the density. So volume we can find out by discharge into the time into the density. So hence we got the how much carbon is required. So this is my first part. Then how much water will be treated? So how much water will be treated will be the total mass of GAC required plus the GAC usage rate divided by the GAC usage rate. So by this we will get the volume of water treated, and then the bed life will be the volume of water treated divided by the flow rate. So by this way we can get the bed life. Okay. So if you want to note it down, I will just go through one by one. So please note down the first part. Now you can go to the next part. So I hope you have noted it down. So now we'll move to the next problem. So the total carbon required was 4.5 into 10 to the power 6 gram and the bed life was 87.5 days. Okay, again a similar problem, but here we are going to calculate the cost. So treated wastewater with flow rate of 1000 liter per minute is to be treated with PAC to reduce the concentration of residual organics measured as TOC from 5 to 1 milligram per liter. The friendly adsorption isotherm parameters were developed and discussed previously. Assuming that the following data apply, determine the PAC requirement to treat the wastewater flow. If PAC cost half a dollar per kg, estimate the annual cost of treatment assuming the PAC will not be regenerated. So the compounds are mixed organics, initial and final concentration 5 and 1, density as 450, Kf value is 150 and 1 by n is 0.5. So we have to find out the total cost. So just note down the problem. It's a pretty direct and simple one. Okay, so very similar problem. So we'll finish it off quickly. So 18th question. So first we will estimate the PAC dose based on the isotherm data. Okay, so again m by v is equal to c naught minus c qe is equal to c naught minus c kf c 1 to the power n. So if we substitute, we will get 5 minus 1 divided by 150 into 1 to the power 0.5. Fine. So this is what it is. So we will get as 0.0267 gram per liter. So this is my m by v. Okay. So this is what I got as the PAC dose. Now the annual cost. The annual cost for PAC treatment, it will be 0.0267 gram per liter, okay, into 1000 liter per minute. So how many minutes per day? We'll just have some unit conversions, and 365 days per year and $0.5 per kg. Okay, and at last we will divide it by 10 to the power 3 gram per kg. So if you do all this calculation, we will get dollars as 7008 per year. So total cost is $7,008 per year. So pretty simple problem. So what we did is, again with the same equation, we found out the PAC dose, that is 0.0267 gram per liter. So the annual cost will be the dosage into the flow rate, and then some unit conversions to get it in terms of dollars per year. Okay. So this is pretty simple. So all these three problems were somehow connected with each other because the same kind of equations were coming in. So there are basically two or three equations in this. So if you know them, you can attempt any problem. And some concepts of mass balance is also required because it is getting partitioned liquid phase and solid phase. So like that, all these problems can be solved using by knowing just 2 to 3 standard equations. Basically all the adsorption isotherm, whatever isotherm is given, so please take care into the consideration and then solve the problem. Okay, so I hope you have noted down. We'll go to the next problem. So $7,008 per year, which is actually very high. So that's why we generally don't go for this kind of adsorption very initially. In some of the specialized cases only we use, because this very high cost associated with it. Okay, so now another problem. So for the experimental isotherm data given below, find the Freundlich and the Langmuir isotherm parameters. So till now we had all the questions related to the Freundlich isotherm. So here we have both the Freundlich and the Langmuir isotherm parameters. So we will compare and we will apply the linear regression to determine the isotherm parameters. So experimental data is given, what is the carbon type, what is the size, what is the chemical, what is the temperature, pH, and the equilibrium time. So we have the sample number, we have 6 samples. So the liquid phase concentration and the adsorption phase concentration both are given. Okay, so we have to find out all the isotherm parameters like Kf, 1 by n. So whatever are the parameters of a particular isotherm, we have to find them. So let's see how to solve this problem. So please note down the problem. We will move forward then. Okay. Okay, so let's see how to solve this. So question number 19. So let's start with the table. Okay. So we have the serial number, the concentration in the liquid phase, and the adsorbed concentration. Okay. So 1, 2, 3, 4, 5, 6. So these are 23.6. So we can use Excel, so that would be much helpful to carry out all this. So I'll briefly tell you how to do it. So this is what is given in the question. So the first parameter that we have to find out to make the isotherms is nothing but Ca by Qa. So in the Excel, if you just give the command equal to this cell divide by this cell, we will get the answer here. Okay, so I'll write down the answers. So only Ca by Qa is required for the Freundlich isotherm, but we will also for Langmuir isotherm, we will also find two more parameters. So which is just log Ca and log Qa. Okay, to the base 10. So that's why log Ca and log Qa. I'll write the answers for these also. So this you can very easily can do it in an Excel. Okay. 0.77, 0.94, and if we see the QA log values, it will be 2.8674, 2.6532, 2.502, 2.082, 1.93, 1.8796. Okay, so these are all the log values. So by using these values, we will plot the graph. So first we will do it for Freundlich isotherm, or rather, okay, we can start with the Langmuir isotherm. So Ca by Q is actually required for Langmuir isotherm. Fine. So if we plot the graph between Ca by Qa on the y-axis and Ca in the x-axis, we will get some points like this. Okay. So suppose these are my points. Okay. So once we get these points, we will try to fit it with the help of a linear regression. So my linear regression will be somewhere like this. It will be somewhere like this, and if we try to find out the equation of this with the help of Excel or by linear equation also, so we'll get y is equal to 0.00127x plus 0.0033. So this is the equation of line of my linear regression line. So here this part will be my slope and this part will be my intercept. Okay, so both my slope and intercept we have got. So if you see the Langmuir equation, so the main equation is Ca by Qa is equal to 1 by Ba Qm plus Ca by Qm. So this is my general Langmuir isotherm equation. So we know from our equation is slope is 0.00127 and it is equal to my 1 by Qm. Okay, so here this is the slope. Here this is the slope. So my Qm value will be 787.4 micromolar per gram. So this is my first parameter. Directly from slope we can get. Okay, so this is nothing but y is equal to mx plus c. Okay, so my m value is 1 by Qm. C value is directly we can get from the intercept. Okay. So Qm we can also write it in terms of 787.4 per gram into 131.39 mu g per mu molar. So it will be 1.03 into 10 to the power 5 gram per gram. Fine. So we found Q1. Now the next intercept. Intercept is nothing but 1 by BAQM. So just a small correction here. CA is my X. So 1 by QM, like this term 1 into Ca by Qm. So 1 by Qm will be my m value and my intercept will be 1 by Ba Qm. So whatever I told earlier was incorrect actually. So my slope value will be 1 by Qm and the intercept value will be 1 by Ba Qm. Okay, so this is how it is. So let me write it once more. So we have Ca by Qa is equal to Ca by Qm plus 1 by PAQM. So this is actually equal to y is equal to mx plus c. So my m value will be this one and my c value will be this one. Okay, this is my x. This is my x. Fine. So the intercept is, so we have already found out the qm. So my 1 by Ba into qm will be 0.00333 gram per liter. So what will be my Ba? Ba will be 1 by 0.00333 gram per liter into 787, the qm value 0.4 per liter. It will be equal to 0.318381 liters per mu molar. So this will be my Ba value. Or I can also write it as Ba is equal to 0.381 liters per mu mole into 131.39 mu gram per mu mole. So it will be 2.9 into 10 to the power 3 liter per mu g. So I can also write Ba in terms of this. Okay. So just with the help, so we will just plot the graph between Ca and Qa. Ca by Qa and Ca will get the curve. So that curve will be in terms of y is equal to mx plus c. We will get the slope, we will get the intercept, and we will calculate the corresponding values. So my m term was 1 by Qm and this one was 1 by Ba Qm. Okay, so this is what it is about the Freundlich, about the Langmuir. Now if you do for Freundlich, okay, so here again we will make a graph between log Ca and log Qa. So if you make a graph like this, okay, so again we will plot it, add a trend line, and we will get y is equal to as 0.4327x plus 2.2831. So here this is my m, this is my c. Okay, now again if we see the Freundlich isotherm equation, so it is log QE is equal to log K plus 1 by n log CE. So this is coming from Q is equal to Kc 1 by n. So if we just put log in both the sides, we will get this equation. Fine. So again, this is my slope m, this is my intercept c. So y is equal to mx plus c. This is my m, this is my c. So simply we can write slope is equal to 1 by n and the value is 0.43, and log k is equal to the intercept, which is 2.28. Okay, so we can write it as k is equal to 190 mu mole per gram into liter per mu mole to the power 0.43. So I can write it as 190 mu mole per gram into 131 0.39 mu mole per mu gram per mu mole into 1 milligram per 1000 microgram into, so these units are a bit complex, so just make sure that you're writing the correct conversions. So 1000 microgram per 1 mg to the power 0.43. Okay, so this is the whole K. So we'll get K finally as 59.92 milligram per gram Lg per mg to the power 0.43. So this is my final answer. Okay. So if you can see that friendly isotherm fits better. So nothing much. So just keep it in mind that for the Langmuir term, we will draw a curve between Ca by Qa and Ca, and then find the equation of the term and find out the slope and the intercept. So these are my parameters Qm and Ba. And for the Freundlich term, again we will make a graph between log Ca and Qa. We'll get the equation of the term, and my intercept will be log K and my slope value will be 1 by n. Fine. So in this manner we can simply find out the all the required parameters. I hope it is clear. Okay, so basic equations of this isotherm should be known so that we can get a straight line. So this is the straight line equation for Freundlich, and this one is the straight line equation for my Langmuir. Okay. So I hope it's fine. So this was the final problem. So thank you for attending the session. So the next session on week 12 lectures will be on 12th April 2024 at same time, Friday 7 to 9 p.m. And here is my email ID, saha19akash@gmail.com. So you can access, so you can reach out to me if you have any issues. Fine. So if you, so I think we can close the session now, and we will meet you next time again. Thank you.